the invitation. It's my first time in Natal, and although I've been here for less than 12 hours so far, it looks amazing. And yeah, thank you all also for coming. And I'm gonna talk today about the topic that I like very much, which are semi-definite programs, which arise all over quantum information theory, as Rafael just mentioned. And I also should know that I've prepared some lecture notes to go with the slides, and you can find them on my website. So here is the link. I don't know if you can see it, like the address. I'll make them. I'll share it with some sort of QR code or whatever in the second lecture. I didn't have time to do that yet. Sorry about that. But yeah, just to let you know that all the lectures will also have some lecture notes with them, where you find some proofs and more references and so on. Yeah, I set a bit of an ambitious program for these 3 lectures, but I'm also happy to take it a bit slower. The important thing is that you understand what STPs are and get an intuition of how they work and how to work with them, what they can be used for. And I'm also happy if I don't cover everything I plan to do. I tend to plan way too much for such lectures, and I'm very happy to be slowed down. The important thing is that you get the most out of these lectures, so feel more than encouraged to ask me to slow down or discuss further something that you didn't understand well. And just to give you some sort of overview of what we're going to do, in the first lecture, I'm going to tell you what SDPs are, and why they are very natural from a quantum information perspective, although they actually come from convex optimization. And I'll just write some sort of quantum information tasks that are as SDPs, so that you can get a first feeling as to why you should probably care about SDPs, and the duality theory, which is something very nice about convex optimization problems in general, but we'll focus on SDPs, and how this duality theory gives you a lot of structure as well about how optimal points of these optimization problems look like, how you get certificates. Often these dual problems also have operational interpretations. So this is sort of the story we're going to look at today. And then tomorrow, I'm going to take a look at 2 what I believe are canonical examples of SDPs in quantum information theory, and we're going to really go through them. The first one is going to be the set of PPT states, which are a very useful entanglement criteria that allows itself to be combined in a natural way with SDPs. We're going to look at that. And the second one is going to be slightly less trivial SDP, in the sense that at first, when you look at this quantity, it might not be clear at all that it is an SDP, namely computing the diamond distance between quantum channels. Okay, so we're going to see that sometimes if you're smart and know your matrix analysis well, you can cast problems in quantum information theory that at first do not look like an SDP, like an SDP. And in the third lecture, we're going to discuss how people actually solve these problems in practice, or by that I mean like how your computer solves SDPs, because this is something people actually do. But at the same time, if you go beyond moderate dimensions, your computer starts crying and nothing works. So, and you're going to hopefully understand why, although SDPs are in principle efficiently solvable in theory, in practice, you're somehow restricted to small dimensions. Not small, let's say moderate. So yeah, before we start, maybe just for me to get a feeling of the audience, how many of you have already heard about SDPs, or good to know Richard knows what an SDP is? Yes, okay, so it's like 50-50. All right, good. All right, so let me now tell you what an SDP is. But before that, I'll just set some notation. Hopefully, the objects I'm going to introduce now are not foreign to you, but let me know if they are. I should also let you know that I've mostly based myself on some lecture notes by John Watrous. They are linked in the lecture notes. I think his lecture notes are great, and he has lots of very nice work in this area. And I don't see why one would reinvent the wheel, right? I think this is already a great resource. So just to be open about this, I'm mostly follow. I mean, he does things slightly more generally in the sense that he looks at conic programs. I'm not going to tell you what those are, but the sort of the general structure I'm going to follow is similar to his lecture notes, and because of this, I also adopted his notation for things. Okay, so first of all, we are if x for me, like this calligraphic x, is also always going to be some finite dimensional Hilbert space, and I'm going to denote by L of x like the matrices on that Hilbert space. We're going to call a matrix Hermitian if it's self-adjoint, and something that is going to be central for what we're going to talk later is a definition of positive semidefinite matrices, right? And we're going to call a matrix positive semidefinite, or PSD for short, if when you sandwich any vector like this inner product over here, it's positive, no matter which vector v you pick. And this is, of course, equivalent to all the eigenvalues of the matrix being positive. Now, just the basic notation for quantum information theory. So we're going to call D of x all the density matrices on the space. So trace one positive semidefinite matrices. And we're going to call POVMs thing like a collection of matrices that are positive and sum up to identity, and these can be interpreted as measurements, right? And the probability of a certain outcome is given by Born's rule, so just trace of MA rho. And something that is very important for the rest of this talk is the Hilbert-Schmidt inner product. So whenever I'm writing two matrices X and Y, when I'm doing this inner product, I mean this Hilbert-Schmidt inner product, where you take the adjoint of a matrix on the left and multiply it with Y, and then you take the trace. This is an inner product. It's not very difficult to show that. And if the matrices are Hermitian, you can forget about the star. Any questions so far on the basic notation? Yeah. Oh, okay. Right. So I usually have some sort of identity crisis. I don't know if I'm a mathematician, computer scientist. I don't know what I am, but which means that I take conventions from different places. So I'm not being consistent. So for instance, I usually like to use the star instead of the dagger, which is a math thing. But if I were a true mathematician, I would make this inner product such that it's linear actually on the first argument and not the second one. So I'm all over the place. I'm sorry about that. Yeah, that's just my fault. But yeah, thanks for asking. This is the dagger. Yeah. Other questions? Nope. Okay. All right. So just again, the basics. So STPs are convex optimization problems. So we're mostly going to be optimizing over convex sets. What are convex sets? Well, it just means that you have some set living in some vector space, and then you just take like these convex combinations for any element of the set. It should be this should be in the set again. And most of the sets we care about in quantum information theory are convex. Okay, so convexity appears everywhere. And for instance, the set of density matrices is convex. If you have two POVMs and you take their convex combination, it's convex again. The set of separable states is convex. So again, convexity appears everywhere. And well, often we want to optimize things which are linear over some convex set. So let's say you want to optimize the energy of a certain Hamiltonian or something like this. This is linear in the the Hamiltonian and the density matrix, right? But sometimes you might want to constrain the set over which you're optimizing, and very often these constraints also, again, are convex. So, and most of these elements also have these positive semidefinite constraints, right? So density matrices are positive semidefinite, POVMs as well. So these sort of convexity constraints, again, arise very naturally. And also mean that when you're doing optimization over convex sets and with linear and convex constraints, things are very nice. At least if these objects are very well behaved, and as we're going to see, they have a rich duality theory. So, and just again to set a bit of notation, another important thing we're going to need are maps from matrices to matrices. And again, maybe this might be a bit confusing. I also, for the adjoint of the map, I'm also using the star. Okay, so essentially, if I'm giving this inner product between matrices, right, the Hilbert-Schmidt inner product I showed you a few slides ago, and given that inner product between matrices, I can define the adjoint of a map that maps matrices in some space to matrices in the other space through this formula. So it's the same as when you're taking, like, let's say, the transpose of a matrix, but now we're looking at linear maps that map matrices to matrices, right? And this adjoint map is going to play an important role in what is to come. And another sort of important set of maps are completely positive maps. So we're going to say that some map phi, which again goes from matrices to matrices, is completely positive if it maps, when you take the tensor product of that map with the identity channel on some arbitrary extra space, that guy is going to map positive matrices to positive matrices. Okay, so now is a good moment to stop and ask yourself whether all of these definitions are familiar to you, if you'd like me to elaborate on any of them, because if any of these objects are very foreign to you, it's going to be difficult to follow what comes next. So yeah. Okay, maybe that will be more clear in a few slides when I write down what STPs actually are. But yeah, I should have been more clear there. Okay, but maybe other questions about these objects and what they mean? Yes. Of course. So let's say, let me write maybe over here. So let's take, as an example, let's take phi, and it's gonna map D by D matrices. Now let's make it even simpler. Let's say it's qubits to qubits, okay? No, I should be consistent with the notation on the slide, sorry. So it will be like L of C2 to L of C2. And then I'm gonna define phi of rho could be, for instance, just the conjugation with a unitary. So this could be, for instance, a unitary matrix. So pick your favorite unitary, Pauli X, Pauli Z, whatever. So this could be, let's say, a channel. This is a quantum channel. Now, let's look at what happens when you want to compute the adjoint. So let's follow the formula. So we have some x, L of y. No, this is y. L of x my God, phi of x. And this is, by the definition, trace y, u x u star. And we want to find out what is phi star, right? Well, we know that the trace is cyclic. So one thing I can do is bring this guy over here. So we know that this thing is equal to this. And this is the same as just the scalar product with, right? So we see that, so this is what we will then call phi star of y. So we see that phi star of y would just be like u dagger y. So it's just like, yeah. Okay. Yeah, okay. I was just being lazy and just assuming that they're all self-adjoint. So then it's, yeah. Not necessarily. So these maps will just be defined on any matrix, but we'll mostly, for all I'm doing, I'm only going to care about Hermitian matrices. So yeah, but not necessarily positive or trace one or something like that. Okay, and then maybe just the CP part. So this is also a completely positive map. Why is that? Well, because when you do, like, let's say, if I now look at what happens when you apply this with the identity map on, let's say, some state rho. Now, this is just going to be conjugating with this identity, right? And if this guy was positive, then just conjugating with something like this will still keep it positive. So we see that no matter what we do, we're gonna have something that is like will map positive to positive. So this is why this is a completely positive map. Now, coming up with a map that is positive but not completely positive is something that is slightly non-trivial, and we'll see an example tomorrow. But essentially, all completely positive maps have a similar form. So, in general, if you have a map that is completely positive, so you say that phi is completely positive if and only if it is of the form phi of x is some ai x for some matrices ai. Okay, so this is the so-called Krauss decomposition. So you can always write these completely positive maps in this form. Are the objects a bit more concrete now, or further questions, complaints? Nope. Then let's continue. Huh. Okay. So what are now SDPs? In the next slide, we're going to see a clean definition. But essentially, they are you want to optimize a linear function of a Hermitian matrix, and usually you have linear equalities and inequalities in X. So very linear things and one nonlinear looking constraint. So more concretely, so they look like this, okay? They have actually many standard forms. This is just one of them. But STPs are optimization problems of the following form. You're given some matrix C. Okay, this guy is Hermitian, the AI is as well. And we want to optimize this, which is just a trace of C and X, okay? And we have these constraints over here, namely that the trace of AI and X equals some BI. So these are real numbers, these are matrices, okay? So this is all just a bunch of scalar products, right? So in principle, you don't have any matrix structure here showing up because this is just like inner products. And then the constraint that makes it look more interesting is this positivity constraint. So we're only optimizing over matrices that are positive semi-definite. All right, so this is exactly how one of the ways you can formulate STPs. There are many equivalent standard formulations. This is not the only one. So, for instance, you could have inequality constraints over here, or you could also have more complicated linear matrix inequalities popping up. So there's a lot of things you can do, but this form is sort of one of the forms that is universal. So if someone claims they have an STP, in principle, it can be massaged into something like this, maybe adding a few variables, blowing up the dimension or something like this, but it can always be written like that. So as I said, you have these linear inequalities, these linear equalities over here, and this one non-linear looking constraint, X positive semi-definite. And just going back to your question, when I was like, what are convex constraints? What does that mean? This means that like, if I have some matrix that is feasible, okay, so what does that mean? It means that, so how does this work? Just have to be a bit stronger. Yeah, okay. So this means that if X and Y are feasible, and by feasible, this just means that they satisfy the constraints, right? Then it follows that some lambda X plus 1 minus lambda Y feasible for all lambda in 0, 1. Because you have that trace lambda X plus 1 minus lambda Y times AI is just going to be equal to PI, right? Because they themselves are feasible. And if you take convex combinations of PSD matrices, everything stays PSD. So that's what I meant by convex constraints. Is your question? Okay, good. Right. And STPs can be seen as some sort of, let's say, matrix version of linear programs. So what are linear programs? Maybe you've encountered them before, even if you haven't seen STPs. This is another very important family of convex optimization problems. And they are essentially the same thing. They look, but instead of having the matrices, looking at matrices that are positive semi-definite, you have vectors which have positive entries. Okay, so it's really the natural generalization to matrices of linear programs. And again, why would you sort of expect that this is relevant for quantum information applications? Well, our favorite objects in quantum information usually come with these constraints, right? Density matrices need to be positive, POVMs need to be positive. So it's natural to that constraints like positivity are arising all the time in quantum information applications. Okay, and this thing over here might be a bit mysterious for now. This is the dual of the STP. I just wanted to mention it already, but we'll only see where it's coming from in a few slides. But essentially, given any SDP, which again can be written like this, it has a good friend, its dual, that is given in this form. So here we're optimizing over matrices, right? And in the dual, we're optimizing over vectors. But these, so we're some scalar product between the vector b and y. B is this vector of constraints, but we only optimize over vectors that for which this matrix inequality is satisfied. Okay. And what is very nice in the topic of this lecture is that if you know things about this problem under some mild constraints we'll discuss later, and you know things about this problem, for instance, under some very mild constraints we'll discuss later, the value of this optimization problem gives you is the same as the value of this optimization problem, and any feasible point of one problem gives you a bound on the value of the other. So this is a very rich and nice theory that connects these two, which we're going to discuss soon. And another nice thing about these SDPs is that, again, under some mild constraints, they can be solved in polynomial time in the dimension of the matrices involved and the number of constraints. So this is also something that you can, again, at least in principle, do for dimensions that are not too big on your own computer. There are also standard packages to do this kind of stuff. Yes. Yeah. So it's not really popping up here. We're gonna see how they show up in a few slides. But in principle, there's no y here, right? Other questions? Again, these are going to be the protagonists of the lecture. So, I mean, it's perfectly fine if this looks mysterious, but at least sort of the notation and what it means here should be clear. So, otherwise, you will be lost for the next hours. So, any questions, comments? Yes, thank you. Next slide. So, what is a simple example? Let's say we are given some Hermitian matrix M, okay? And what is an example of an SDP? The largest eigenvalue of that matrix. Okay, so we're gonna see. I mean, this is somehow the simplest of all SDPs because it kind of only has a trace constraint and the positivity constraint. So by the variational formulation of the eigenvalue, you can write the largest eigenvalue of a matrix as the maximal trace of that matrix with the set of states. Okay, so this is just one characterization of the largest eigenvalue of a matrix when it's Hermitian, and this is an SDP. So if you go back to the former slide, we only have one constraint, which is that with the matrix being the I1, say, the identity matrix, and B1 being just 1. So, right? And this positivity constraint. So, yeah, you see that eigenvalues are indeed an SDP. This is not how you should, of course, compute the eigenvalue. It's just to connect it to things you're familiar with. But you do get something out of the I'll just state the dual, and later we'll see like why this is actually nice. So if you go through the formulas I showed you before, the dual will be this problem. We just want to minimize the parameter lambda such that lambda times the identity is greater or equal than the matrix M, which is another characterization of, so so that if you can find a lambda such that lambda times identity is greater than the matrix M, you get a bound on the largest eigenvalue, right? So this sort of idea pops out immediately from SDPs. Okay. let's maybe look at questions on this example. Yes. Yeah, but we're going to see in a few slides why. So if that's still a bit mysterious, that's fine. Minimize. Yeah, yeah, yeah. Yeah, 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 yeah. But maybe just one more, slightly more complicated problem, which has a more quantum information theory flavor. Okay, so let's say we're given a bunch of states row A, so density matrices 1 to K, and they appear with probability PA. And we want to choose a POVM that maximizes the success probability of us sort of identifying which state we got. So just to give you a better idea of, or sort of an idea of what's going on. So we have Alice that samples some A, some index A with probability PA. She then prepares the corresponding state, row A, which she sends to Bob. And Bob is supposed to measure some POVM MA, which he's allowed to pick as he pleases. Okay, so he has complete freedom to choose his POVM. And he has to output a guess of what Alice was sending him. So he has to infer what was the label A from the outcome of his measurement. And the rule of the game is that Bob wants to maximize his probability of actually guessing the correct label A. And this is a very natural task in quantum information theory. It's like some optimal distinguishability problem, right? And then what is the objective function? What is the probability of that A hat, which is the output guess of Bob being equal to A? Well, if you use the Born rule, you see that it's going to be given by this formula. So MA is the POVM, PA are the probabilities, which Bob knows, by the way. So he knows with which probability, like he knows both PA and row A, and he wants to maximize this thing. And this is again an STP, because our objective function can be written like this, okay? And now we have this this sum over here. So we have these constraints here. Our objective function is this sum of traces of MA with the row A. Again, the row A are given. And these guys have all to form a POVM. All right, so we know that the MA have to sum up to the identity, and they have to be positive on their own. And you might now protest and say, hey, Daniel, you told me that STPs look like this. And now, like, where are the traces? Like, why are the constraints written like that? And as I told you before, once you start working with STPs, you see that there are many equivalent ways to formulate them. So I'm just going to take a few minutes to show you why, sort of, how to massage these constraints into precisely constraints of this form. Okay, so the first trick, and this is a trick that is quite useful when massaging things into STPs. For simplicity, I'm just going to consider that K equals 2. Okay, so we only have 2 states, but hopefully you'll see how to generalize things. So we have the constraint MA greater or equal than 0, but now we have actually 2 matrices, right? And before, we only had 1 matrix, like we only had like X greater or equal to 0. Does anyone see how we can actually define some new optimization problem that sort of takes care of this constraint here, but only requires one matrix? I don't know if what I asked was very clear, but Yeah, I see some noddings. Do you have a suggestion? Yeah, I'm seeing people doing this. This is the correct idea. Just do a block diagonal thing, right? So instead of optimizing, we double the dimension. When we're doing this on the board, it's fine. When you're doing this in the computer, it will hurt you if you're not smart about it. But let's just keep it that way for now, just for you guys to see what happens. So instead of optimizing over MA, I can just do a direct sum, right? And consider x of this form. So if this matrix, I could call this x, and this matrix, if I impose that this matrix is positive semi-definite, because it has this block diagonal form, then we also know that this is positive semi-definite if m1 is larger than 0 and m2 is larger than 0. So we by doing this direct sum construction, we can enforce many of these constraints at the same time, and we're still like looking like the SDP I showed you before. And now I just have this sort of a constraint like this, right? That their sum is the identity. So I'm saying that m1 plus m2 equals identity. And before we had like the constraints we had before were of the form AI x equal bi. How do you go from something like this to this? Well, do you guys have any ideas how we, by playing with constraints of this form, we can impose something like this after we did this direct sum? So, for instance, like let's just do the diagonal, okay? So we by doing these traces, for instance, we could do something like trace 0, 0. I'm just going to write something. Okay, so this is the same as this, right? So we know that. So essentially, writing a constraint of like this, let's say that saying that this is equal to 1, essentially forces that a certain entry of the matrix is equal to 1. So to go from constraints like this to constraint like this, all we need to do is to introduce a basis for these matrices, right? And take the trace of the basis with the left-hand side and take the trace of the basis with the right-hand side. And then if you have equality for all the traces in that basis, then the two matrices are also equal. So so this is also the standard way how you can, for instance, massage a constraint like this one into a constraint like this one. Okay. There are many tricks like this, and the point I wanted to make here is that it might take some practice to immediately see that you can massage something like this into the standard form I had before, which is this one. And I will not show you all the tricks, but tomorrow we're going to do 2 more that hopefully show you that, give you some practice and show that sometimes it's really not obvious how to do this. But if you play enough with these STPs, you learn a few tricks. Okay, questions about these 2 examples? Nope. Then finally, let's go into the, sorry, I didn't write down the dual. Okay, so essentially, if you play around, the dual will then be looking like this. You want to minimize trace of age such that age is greater than PA row A for all A's. And somehow this age gives you some sort of witness on the on this problem. But let's finally talk about where are these duals coming from and why you should care about them. Okay, so the way they arise is if you look at Lagrange multipliers. Okay, so we're solving a constraint optimization problem. So one way of doing this is to introduce Lagrange multipliers, which are going to be a vector y. So going back to your question, this is where the y comes from. These are like the Lagrange multipliers of the problem. Okay, how do Lagrange multipliers work? Right, you have your objective function, and whenever you look at points x such that this is not equal to 0, then we can make this function over here explode, right? So in some sense, by adding these Lagrange multipliers and optimizing this function, it immediately forces us to look at the set of points where this thing is equal to 0, right? And if you look closely at what this Lagrange multiplier function looks like, you can rearrange it like this. So it's going to be B transpose Y, and then you have the scalar product of C minus yi times these matrices ai, and this is all just linearity, right? I'm just putting this inside here and this inside here. So the first this times this gives me this term, and this times this gives me this term. And so what I'm getting in the end is just a function like this. Okay. And if this thing over here is not equal to 0, then I can just scale x, okay? And we get that this term over here explodes. So we see that for the Lagrange multiplier, not because this term here doesn't depend on y, right? So this is a function of x and y. So we see that for this function, this part of the function not to explode when we're optimizing, this thing over here has to be 0, okay? Which means that C minus yi times ai has to be a positive, minus s, which is just some slack variable, has to be 0. So we see that C minus yi ai has to be positive semidefinite. Okay, so we see that a necessary condition for this thing not to explode is precisely that this inequality holds. I think I made a sign mistake there, right? Or so it should be C minus S greater or equal than 0. C minus blah 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 equals S. S is greater or equal than 0. So yeah, it should be the other way around. Sorry, there's a sign mistake there. But hopefully the main idea still survives. And this is how you get the dual, because it's precisely coming from this Lagrange duality. And we see also that if you have any primal feasible x and dual feasible y, then this inequality here has to hold. Okay, how do we see that? Well, here I fixed my sign mistake, I believe. We have that this matrix here is positive semidefinite, right? So if x is positive semidefinite, then we can just take all these scalar products, and we see that what remains is B transpose Y minus Cx, which is exactly this inequality we wanted to have. Okay, so essentially, by looking at this Lagrange multiplier, we have that no matter what STP we're looking at, if we have a feasible y and a feasible x, then this relation must always hold. So if you have, let's say, your favorite STP, and you want to just get an upper bound, or you want to, and you have a pretty good guess for the dual, then you're already done, right? I mean, maybe you're done if the bound is good enough, because it immediately, at any point y will give you an upper bound. On the other hand, if you're interested, let's say, in the dual, and you want a lower bound, then you just need to find any feasible point in X, and you'll get your lower bound. So if you have a good guess, or if you have a good candidate solution, this already tells you something. And this holds for any STP, doesn't matter what, no conditions required, right? This was just a simple Lagrange multiplier argument. So, okay, this already should tell you a little bit where the dual is coming from and why it's useful, but there's going to be more in a few slides. But any questions so far? Yes, I see you, yeah. Mm-hmm. That's exactly what the next 5 slides are about. Thanks. Yeah. Oh, yeah, I didn't explain that well. Thank you for that. So, so the dual feasibility just requires us that because we can always let's say if let me think about the best way to so essentially if X is not exactly like because this thing over here, right? This has to be equal to 0 for this function not to explode, right? So we can add this additional positive matrix S to sort of correct. So it might be the case that this thing over here is only positive semidefinite, not necessarily like that equal to 0. There might be still some rest there, and this S is taking care of that explicitly, so that this doesn't explode. So yeah, so essentially, if I give you some feasible y, again, sorry for the sign mistake here, but the point is that for this thing not to explode, then this has to be 0, right? So if I give you a feasible yi, then this S will then just be sort of whatever is left to make this 0 and not explode. But I'm giving myself freedom here. So for instance, if yeah, maybe I won't. If I say more, I think I'll confuse you. But you can also, you have some freedom in S. For instance, if X is not full rank and things like that, because S just need to be chosen in a way that this doesn't really explode. And in particular, you can choose it in a way that you can always choose it like this. Further questions? Okay, if not, then let's go address your question. And there is this one very nice theorem, which is called, well, it's a condition actually, not a theorem. Sometimes I usually call it Slater's theorem or Slater's condition, doesn't matter. The point, and this doesn't only work for STPs, it works for more general convex optimization problems, but we'll specialize to STPs. And it is one, and I would say like it's the main condition people use to answer his question, which is like, when are the values of the primal and the dual the same? And it tells you that if you have a strictly feasible point, okay, by which I mean that you have a full rank matrix x0, strictly positive, that satisfies all the constraints, then there is no so-called duality gap. And by duality gap, people just, if you see that term, people is just like the difference between the maximum over x and the minimum over y. Okay, so essentially it's saying that the value of the primal problem is the same as the value of the dual problem. So if you can solve one or the other, and this thing is satisfied, then you're good. And here, it should also be said that once you're given this, you have also that the dual optimum is attained somewhere. I will not prove this. This is probably the most difficult thing we're gonna do in these lectures, in the sense of like actually proving it. The lecture notes have a proof. It's not like insanely difficult, but it's fine if you don't feel like looking at it. I myself wouldn't be able to immediately like write down the proof. But it's very useful. It's definitely something you should know how to use. And many quantum information theory papers don't bother to check this thing, which sometimes annoys me. Because it's they didn't just say like, oh, the value of the max of the primal is the same as the dual. This is not always the case. In the lecture notes, you also find one qubit example. Usually this happens when, I mean, this already tells you what needs to happen is that like all feasible points are somehow rank deficient and things like that. So if when there's some weird things going on with the rank of the feasible points, this is not required to happen. But most STPs we look at in quantum information theory are nice. Usually, if you just try with the maximally mixed state, something nice happens already. Or let's say if you're optimizing over POVMs, just pick the trivial POVM, and it usually works. Or just like you take some feasible point and you perturb away with the maximally mixed state with some small epsilon. So these are all standard tricks. Again, these are not all tricks, and if you start working with STPs, you actually get a hang of it. There are many others, but usually it's not a problem, but it's something that needs to be checked. Okay, so yeah, okay, so this is what I just complained about. Another thing that I think is swept under the rug, and this is just me complaining again, it's not a real problem in practice, is that if people often just claim that STPs can be solved in polynomial time, but actually that comes with some asterisks as well. So for instance, as we're going to see in the third lecture, you also need to know, for instance, a bound on the radius of the feasible set. So if your feasible set is, let's say, double exponential in size, in the dimension, then the STP might not be solvable efficiently. And people can construct such badly behaved STPs. I will complain less about this than the Slater condition, because in quantum information theory, this is usually not a problem. Again, we're usually optimizing over the set of states or the set of, let's say, POVMs. And well, the set of states already tells you, you know that the radius of that state, that set is 1. So that will not be really a problem. So, but in principle, if you're looking at more advanced STPs, so some of you might have heard, for instance, about the NPA hierarchy of sums of squares. There's some details about that in the lecture notes as well. So if you leave the sort of very nice quantum information theory STPs and look at harder optimization problems, then you should also care about this. Okay, so the main message is there are some asterisks when you're using both duality theory and when you're saying that you can always solve STPs efficiently, and we should care about them. And last but not least, in the 5 minutes I have, I just wanted to say the last is one other nice property of STPs, which is complementary slackness. Okay, so duality theory lets you map solving one STP into solving that dual problem, again under Slater's condition and so on. But you can also get structure about optimal points from this convex optimization theory. And this is also something very useful to know. And tomorrow we're going to see this in practice. Okay, so this still might seem a bit abstract. Tomorrow we're going to see concrete examples how you use all of this machinery. But the nice point is that if you have strong duality, and so for instance, Slater's condition I just showed holds, and you have your optimal points, okay, then you have this thing. So, oh dear, I realize I have not defined what A is. I'm very sorry. So this A star of Y is just the map that maps your vector Y into this thing. Okay, so it's just like it maps the vector into the linear combination of matrices. Okay, so if you know, it has to satisfy this condition. So if you look at the optimal minus this matrix C, we'll just call this the S before, then we know that the product of S with X actually has to be 0. So this gives you some extra information about how optimal points look like. And you can use this both to certify optimality, but this gives you a structure for optimal problems. So if you go back, for instance, let's say this state discrimination problem we talked about before, this gives you some equations about how the optimal measurements look like and things like that, which can then be useful in certain quantum information theory tasks, because you know, like, oh, the optimal satisfies this and that, so this gives you more structure. So this is another nice thing about duality theory, that you have this what people call complementary slackness. You find the proof in the lecture notes. Okay. So just the takeaway message before we go to the coffee break. So most of the things we care about in quantum information theory have both this convex structure and the positivity constraints baked into them. So and we often want to optimize linear functions of matrices. For instance, when you were looking at the largest eigenvalue problem, or the sort of optimal distinguishability function, these are both linear. So these scenarios pop up all over quantum information theory, and this is why STPs are very natural to consider in our field. Then another thing you should take home with you is that given one STP, you always get its sibling, the dual problem. And the dual problem will tell you a lot about the STP, namely that if you find a feasible point of the dual, it will give you a bound on the optimal value of the primal and vice versa. When are they the same? One, your go-to method to check if the dual and primal values are the same is Slater's condition. And last but not least, once you have that the dual and the primal are the same, say you checked Slater's condition, then you also get more structure, some extra equations hold for the solution, and the name of that is complementary slackness. So yeah, this is it for the first lecture. As I said, later today, we're going to look at two very concrete examples, namely PPT states and the diamond norm STP. But for this was all. Any further questions? Yes. The lecture. I put them on my website, but I did not link them properly yet. So here's the. I guess. Oh no, this is. So can I maybe? I guess it's impossible to read this link, right? Or is it possible to read it? I should be doing. So they are already there. They're just not linked properly on my website. I didn't find the time to create the web page and so on. But if you go to that link, they're there. Also the slides. And I think I'm only going to talk again after lunch, so I'll work on that during the next. Yeah. Other questions? Yes. Real complex. I mean, if you have matrices with entries in finite fields, then even these very nice, I mean, some of these problems can become very nasty and NP complete or and so on. So duality. I mean, I guess I for instance. Like positivity constraints and so on, it's not very clear to me how you define them immediately if you have a finite field. I don't know. Do you have a particular definition in mind? Okay, okay. Yeah, so I think these sort of PSD constraints don't go well with finite fields. That is at least my first reaction. I've never, but this is just my first reaction. I have actually never um, seen a reasonable definition of let's say PSD over a finite field. I don't know. Does anyone in the audience know of a good definition, or because I mean, if the field, let's say, has some finite characteristic, then yeah, some these notions are a bit strange to me. But do you have a comment or? Yeah. I mean, but you can. I mean, like linear programs, for instance, make sense for like finite fields. But I can think of a formulation that makes sense. But SDPs, like these semi-definite constraints, I think the PSD order. I don't know. I'm talking about the honest answer is I don't know. I'll look up whether there are reasonable definitions of let's say PSD constraints for finite fields, and I'll let you know in the next lecture. Yes. Uh-huh. Mm-hmm. 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 Yes. So that can happen. So for instance, for the example in the lecture notes for a problem where duality gap exists, it's precisely of that form. I mean, I have them up here, so maybe I just show it to you if you're interested in that. So it's actually not a very complicated example. Where are yeah, so it's this problem. Oops. Over here. So essentially, so the primal problem is this one. We want to minimize. Now let's say that our matrices are real. Okay. So we want to minimize 2 times the upper right entry of the matrix. This is clearly linear, and we impose that x11 is equal to 0. Okay. So if x11 is equal to 0, then to keep the matrix positive semi-definite, the upper right corner has to be 0 as well. So we see that the value of this guy is 0, because the only feasible point is really the 0 matrix. Okay, and if you do follow the recipe of how to build the dual, then you you get that the dual is infeasible. Okay, so essentially the constraint, the dual looks like this. You want to maximize 0, subject to the condition that this holds. For Z, a positive semidefinite matrix, but you cannot make this happen, because if Z is just quick argument, you can combine Z, a positive semidefinite matrix, with this matrix Y, but you need to make the lower right corner 0. So Z has to have a lower right corner 0 as well, and then you cannot also have a 1 here, right? So this is infeasible. So this guy explodes. The primal doesn't explode. It's feasible. So here you have an example of that happening. And well, why the Slater condition doesn't hold? Again, all the feasible points of this, the only feasible point is the 0 matrix, which is of course not strictly feasible. But yeah, if you want to go to the lecture notes to look at that more carefully. Okay, more questions? Nope. Then yeah, thanks.